Hello and welcome back to me answering questions from Algebraic Geometry by Robin Hartshorne. Today I will be answering question 2.6 of section 1. So let's begin. Firstly, this asks us to show that the dimension of a projective variety plus 1 is equal to the dimension of its coordinate ring. First, S of y is an integral domain which is finitely generated over K. Thus, its dimension is equal to its quotient field. The dimension of S of y is equal to its quotient field, the transcendence degree of its quotient field. Next, what we want to show is now the quotient field of S of y is the exact same as the quotient field of S of y localized at a point F if F is not equal to 0. Furthermore, this is also an integral domain. Therefore, if F is not equal to 0, then the dimension of S of y, F is equal to the dimension of S of y. Now, as y is a projective variety, it is non-empty. So there exists some index with y intersect uj non-empty. Without loss of generality, assume this is 0. What this means is that y without the hyperplane defined to be the 0 set of xj is non-empty. And it also means that the ideal generated by x0 here is not a subset of the ideal generated by y. Thus, x0 is non-zero in S of y. And the dimension of S of y is equal to the dimension of S of y localized at x0. Now, define y0 to be equal to the image, I will use the other type of phi, the image of on not, whoops, phi naught of y intersect u0. This is homeomorphic on u0, so the dimension of y0 is equal to the dimension of y intersect u0. I'm using naught here because the coordinate functions look prettier when I define an explicit homeomorphism, explicit ring homomorphism. So consider A of y0. We can define a function, let's say psi from A of y0 into, not mapping into, oh god, into, let's just say S of y localized at x0. via f of x1 dot 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 xn mapping to f of x1 over x naught, comma dot 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 xn over x naught, which is equal to what we wanted to. Sorry, which is equal to beta of f multiplied by x naught to the minus degree f, i.e. the degree of psi of f in this ring is always going to be 0 because it's in Hartshorne he says E, but then this is E minus E, so it's always going to be 0. Thus, the image of a y naught is a subset of the subring of this localization whose degrees consisting of elements of degree 0. Now, this is additively generated by the monomials m of the form x1 to the a1 dot 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 to xn to the an all over x naught to the a1 plus dot 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 plus an, which is equal to x1 over x naught to the a1 multiplied by dot 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 multiplied by xn over x naught to the an, which is equal to the image of the element x1 to the a1 multiplied by dot 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 multiplied by xn to the an. Thus, we also have a double inclusion. Oh my goodness. Thus, we have the additive generators being the image of what we have here. So s of y localized at x naught, the degree 0 elements. So the image of our psi is equal to sy x naught. Let me remove one of these things. So what we have is that we have its surge activity on what we want, or what Hartshorne tells us to want. But do we have injectivity? And the answer is absolutely yes. A function is injective if and only if its kernel is 0. And we are essentially multiplying our f by something which is non-zero in an integral domain. Therefore, yeah, no, it's the kernel of psi is going to just be 0, which gives injectivity. And this works even for mappings of modules, because the category of ring modules over any ring is an abelian category. Anyway, moving on, so we have a of y naught isomorphic to the degree 0 elements of s of y localized at x naught and the degree 0 elements. Well, something within SYX0, localized at X0, is going to be f multiplied by x0 to the n, where f is of degree 0. Essentially because if we have something of degree n, we can bring it down by multiplying by x0 to the minus n, and vice versa, so we can just have this. I need to add a dot there. And obviously there's the things of negative degree within our localization, which it's quite bad that Hartshorne asks us to do this without introducing localization. I think he does that in chapter 1.3. Anyway, he assumes that you already know it. Is the one thing. He just does not want to get bogged down in the localization in any real deep algebra. That's why he adds so much from Mattia MacDonald and from others like Oscar's, from, oh, I've forgotten who Zariski collaborated. Is that the right word? I don't think it is. Oh dear. Ah well. But the negative degree bits correspond to minus n. So S of y localized at x0 is isomorphic to the subring of degree 0 elements. Adjoin x0, and this gives us all the positive degree elements. Adjoin x0 to the minus 1, which in itself is isomorphic to a of y0 adjoin x0, x0 to the minus 1. Now, what we want to see is this an integral domain? At which point we can use the same trick we used at the very start. Well, they are. It is. Corollary 2.3, so tells us that y0 is an integral domain. So the dimension of a y0 adjoin x0, x0 to the minus 1 is equal to the transcendence degree of k of a y0 adjoin x0, x0 to the minus 1 over our field. However, this is the same as this. So the dimension of this is equal to the dimension of just a y0 adjoin x0, which is very easy to see to be the dimension of a y0 plus 1. Now, this is true for any non-empty. We just said without loss of generality assume that. So we just assumed y intersect u0 is non-empty. So this is true for all j with y intersect uj non-empty. Now we use y is covered by the open sets y intersect ui. Thus, by question 1.10b. The dimension of y is equal to the dimension of, or the supremum of that, of the dimension of, supremum of the dimension of y intersect ui, or the supremum over I, which is equal to the supremum of either 0 or the dimension of a, or rather, sure, a, hmm, ah, yeah, dimension of a I, which, to be honest, 0 can be. But this is constant on any non-empty for all j with y intersect uj non-empty. The dimension of s of y is equal to the dimension of a y j plus 1. The dimension of our projective variety is equal to the supremum over I of the dimension of yi, which is equal to the supremum over I of the dimension of ai, which is either 0 or the dimension of this minus 1. Now, what we want to next see is that the dimension of sy cannot be 0. But why? We want to essentially show this fact. Ah! Y is non-empty, but this would imply that I of y were equal to the ideal generated by, well, this would imply that I of y was the irrelevant ideal. Therefore, this cannot be 0, and the dimension of s of y must be at least 1. So, the dimension of, well, if it is equal to 1, then it's the supremum of 0, in which case it's the dimension of s of y minus 1, or it is equal to the dimension of s of y minus 1. Therefore, the dimension of y is plus 1 is equal to the dimension of s of y. And we are done. Thankfully, tomorrow's is an easier question. Thank you for watching. As always, this is me. Okay, goodbye.